Matrices solutions are another way to solve linear equations. Since systems of linear equations occur in so many practical situations, computer methods have been developed to efficiently solve linear systems. Computer solutions to linear systems depend on the idea of a matrix, plural matrices, a rectangular array of numbers enclosed in brackets. Each number is called an element of the matrix. Gaussian elimination is the method used for solving linear equations using matrices. As an example, start with a system and write the coefficients of the variables and the constants as a matrix, called an augmented matrix of the system. We have the system x plus 3y plus 2z equals 1, 2x plus y minus z equals 2, x plus y plus z equals 2. And notice the first row of my augmented matrix is 1, 3, 2, 1, just like this first equation. Second row is 2, 1, negative 1, 2, and the third row is 1, 1, 1, 2. We usually draw this line in this augmented matrix to separate the variables from the constants. Notice these were all x, y, z, and constant. The vertical line, which is actually optional, separates the coefficients from the constants. Because this matrix has 3 rows horizontal and 4 columns vertical, we say the size it's a 3 by 4 matrix. The number of rows is always given first. To refer to a number in the matrix, use its row and column number. Solving with these matrices, we do matrix row transformations. In the augmented matrix, the following row transformations result in an equivalent system. We can interchange any two rows, and we'd abbreviate that row I interchange with row J. We can multiply every entry in a row by the same non-real zero number, just like multiplying an equation. So A times row I becomes the new row I, means it replaces. And we can add a row of non-zero multiple to a non-zero multiple of another row. So we can say we're going to take row I and add a number times everything in row J to row I. So in Gaussian elimination, these transformations are just restatements in matrix form of the transformations of systems used to solve systems by elimination or addition. From now on, we refer to the third transformation, a multiple of the elements of a row. We'll abbreviate it as a multiple of a row. When you're doing Gaussian elimination, it's a systematic technique for applying matrix row transformations in an attempt to get a matrix in diagonal form. And this is diagonal form for a system of 2 equations. Notice we have 1, 1 in the diagonal, and then we do have numbers here for the consonants with zeros. For a system of 3 equations, we still have 1s on the diagonal. Everything else is 0, and then the line argumented, we have some constants. Then the solutions are ready to obtain, because this means 1x equals A, 1y equals B, and 1z equals C. This is called reduced row echelon form. The steps for doing Gaussian elimination to get it in diagonal form. Obtain 1 for the first element in the first column. Use the first row to transform the remaining entries in the first column, or using that first row to make the rest of the things in the first column a 0. Then we get 1 as the second entry in the second column. We use that second row to transform the remaining entries in that second column to 0, and we continue this manner as far as possible, depending on how many rows there are in our matrix. For Gaussian elimination, proceeds column by column, essentially, from left to right. That way, when you're working with the second column, no row operation will undo the form in the preceding in the first column. So let's do. First, we have to get the equations in the same form, x, y, and then equals the constant. That has to be the same to begin with. Then to make our matrix, we will start out with 3, -6, 9, and 2, 1, -4. We want our goal is first to get this number to be a 1. And since I notice this whole row is multiples of 3, I'm going to take row 1 and divide it by 3. You should mark down what you're doing on each step. So that gives me 1, -2, 3. And then the second row is going to stay the same. Now the next step, since we've got this 1 here, is to use row 1 to get a 1 here with row 2. So what I'm going to do is take row 2 and I'm going to subtract 2 row 1s from that. So 2 row 1s would be 2. This 2 minus 2 will give me a 0. Well, row 1 is going to stay the same. And then here, -2 times -2 will be 4 plus 1. This will be 5. And -2 times 3 will be -6, and the -4 will give me -10. I've got the 1 and the 0 here that I wanted. My next thing I need to do is get this to be a 1. So I think the easiest way to do that, I'm going to take row 2 and divide it by 5. Row 1 will stay the same, this transformation, and row 2 will become 0, 1, -2. I'm going to recopy that row over here just because I ran out of room and I want to make sure we're clear what my next steps are. So that was just a recopying. Now I want to use row 2 to get this to be a 0 in row 1. To do that, I'm going to take row 1 and I'm going to add 2 row 2s, since 2 and a -2 will give me a 0, the 0 that I need. So row 2 is going to stay the same. Row 1, 0 times 2 plus 1 is still 1. 2 times 1 is 2, plus the -2 will give me 0. -2 times 2 will be -4, plus the 3 will give me a -1. And now that I have this in diagonal form, I can say that x equals -1 and y equals -2. I can give that as an ordered pair, -1, -2, and this would be an independent system of equations.